All right, so I'm Allan Deutsch, and I'm here to tell you guys about Lambdas in modern C++ and also template metaprogramming. Does everyone here know what a lambda is? You do? Okay.
Allan, what are lambdas?
Lambdas? That's a great question, Riff. So today we're going to have 54 slides all about lambdas, except these first two, which weren't really about lambdas. So that's what we're going through. So for lambdas, they're new in C++ 11. So before 11, you don't have lambdas. And then in 14, there's some extra features that lambdas get that isn't available in C++ 11. So I'll be covering some of those differences as well. So it'll start out pretty simple, like what is a lambda? What are the little components of it? How do they work? Simple stuff like that, and ramp up into more complex topics, such as how to do some weird template metaprogramming stuff using lambdas. So don't wait until the end for questions, because if you have a question on some of the basic stuff and you don't get it answered, you're going to be totally lost when we get to more advanced things. So just ask your questions whenever you have them. And hopefully you'll learn at least 3 to 5 super neat things. Cool. So what is a lambda? Sort of a function. It's an anonymous function, which is an unnamed function, or a closure or a callable object. Different languages have different terms for them. But ultimately, it's some sort of function that isn't a named function, but can still be invoked, possibly with parameters and a return value. So the anatomy of a lambda, it has 3 main parts. So the first one here is the capture list. That's in the square brackets. The second one is the argument list, which is in the parentheses. And then the function body is in the curly braces. So that right there is actually valid C++ code. It's just empty braces. So it's really fun to type because you just have all these braces. The only one that's missing is the angle brackets, and there's no templated lambdas, so you don't get those, unfortunately. Maybe you can do some comparisons. So the capture list is basically variables that you want to have access to in your lambda function without necessarily having to pass them in as arguments to the parameter list. So for example, you can capture by reference. You can capture by value, just by having your variable name with or without an ampersand. There's also automatic capture. So if you use an equal sign, it'll automatically capture anything you use by value. And if you use an ampersand, it'll automatically capture by reference. And then you can also capture the this pointer. So that just kind of works the way you would expect it to. So in C++ 14, but not in 11, you can also have assignments. So if you want to have a named variable within your lambda and initialize it with some value other than what that name is, you can do that. So var equals 1 would be an integer with the value of 1. You can also do that with references. So in that second one, var would be a reference to p. So some notes about it: you can capture multiple values. You're not limited to one. The automatic captures only capture what is used. So if you have an equal sign, it's not going to just copy every value that's visible to it in scope at that point. So that's nice. You also don't have to capture anything. And there are some cool things you can do with lambdas that don't capture at all that you can't do with ones that do capture. And then captures obey normal lifetime rules. So for example, if you capture a reference to something on the stack and then you pass your lambda after that stack gets exited, then whatever you have a reference to is now a dangling reference. And so you're going to have all sorts of issues if you try to use it. So just be aware of that when capturing by reference. You shouldn't always just default to by reference, especially if your lambda is going to live longer than wherever it's created. So the parameter list works kind of like a normal function. You can pass it values or arguments by value, by reference, by const reference, however you want that you would normally do it. But they're not quite a regular parameter list, because in C++ 14 we get generic lambdas, which are the lambda solution to templates. But rather than being templates, they use auto. So there's no ugly syntax. So you get to do cool stuff like this, where you just say auto val, and it'll just figure out what auto is without all of that extra template boilerplate you would have on a regular function, which is super nifty. And it works pretty much the way template type deduction does, except using auto keyword. There's a few small differences, but they're not super important. If you want it to be const, use const auto. If you want it to be a reference, use auto ref, whatever. pretty much the same. For the small differences, see the Effective Modern C++ book by Scott Myers. He goes into a lot more detail on what those differences are between auto and templates. So if you're interested in the really, really nitty-gritty stuff, then that's a really great reference for you. So in the Lambda function body, they're pretty much just like normal functions. They can use any variables that are in the capture list. Anything that's passed in as a parameter, it can use those. All of the globals that are visible to the Lambda are accessible to it, and it can return values. So pretty much a normal function. But of course, there's a catch. It can only have a single return statement. And so the return type would be whatever is the type of the resulting expression in that return statement. So you can have other code in your Lambda, but there can only be one return. Otherwise, it'll return void, obviously, if you don't return anything. So it follows the auto return type deduction rules. But in C++, so here's some examples of them. So like if you add an int to a float, that expression resolves as a float, so it returns the type float. Returning an OStream reference, if you return two operations that are enclosed in parentheses and using a logical operator, then it'll return a bool. So pretty straightforward, what you would expect. Then in C++ 14, the rules for this return type deduction got relaxed a bit. You can have multiple return statements as long as they're both returning the same type or things that can be implicitly converted to the same type and the compiler is able to figure it out. And the return type is just deduced using auto return type rules. So the same as if you had a function that was returning auto in C++ 14. It's pretty straightforward. It'll usually do what you expect. So an implementation of a Lambda, you generally want to store it unless you're passing it in as like a functor for a parameter to something like as a comparator. So you would have, generally the type is going to be auto for your Lambda variables because you don't actually know what the type of it is. You might think that you know from the signature, but that's actually not the type. So you can't just like call it a function pointer. So other than that, you have your capture list, which may or may not be empty, your parameter list, which also may or may not be empty, and then the body of your Lambda. So it looks pretty similar to a regular function declaration, not that different. So the way that it works under the hood is that the compiler is actually generating a struct like this with some sort of garbage name, and then it has an operator overload that corresponds to your Lambda. So this one happens to be returning an int plus an int, because those are the parameters. So it reduces that the return type is int, and then it creates an instance of that struct for you called whatever you named it. So you can see back here I named mine add, so that's what we get here. So yes, question?
Captured values, so that when you made that assignment to auto, those captured values, if you change them within for example, every time you invoke the Lambda, if they change, are they maintained, for example, in the next use and use after that? Or?
Okay, so the question is like when you're capturing values, if they'll be maintained. And so in this case, since I'm storing it into a variable, those captures will happen when the variable is initialized. And so if they're captured by reference and they change, then since it's referencing that variable, it would change. But if they're captured by value, they wouldn't be changed. But if you were to like create another instance of this Lambda at a later point, then it would like using these capture list again, not just like copying the Lambda object itself, then it would be the new values, whatever you're passing in the capture list. But if you're copying the Lambda, like if you copy add, that object there, then it would be whatever was captured by add. So it wouldn't change them.
And if you captured by value and the actual like enclosure itself modified those values will stay as modified in future uses of that Lambda?
It depends. Yeah. So the implementation of a Lambda is basically some sort of throwaway construct made for a specific task. Generally, it's used in one place, like you're passing it in as a comparator for a sorting algorithm or something. So it's code that you really only use in one place, one time. You don't need to structure it super well and have your typical OOP principles because it's not going to be code that's reused a lot. So the two, like a Lambda and that instance of a function object, are pretty much the same, except the Lambda is just kind of syntactic sugar, so you don't have to type as much. And it's more clear that it's something that won't be reused a lot. So some examples of Lambda functions. Here we have square, which just takes an integer and returns the squared value. And then square float, which squares a float, kind of the same thing, just like you would have with regular functions. But then in 14, you get to use auto, and so then you only have to write one square, and it'll work for all your types. Yay. And then you can have something like double, where it captures the value by reference and then doubles it. So that's reasonably straightforward again. Pretty much going to do what you expect. So lambdas are not super complicated. They can also return other lambdas, though, which is pretty neat. So you can have a function object. Here we have add. And then when you pass it an integer, it'll actually give you a capture of a lambda that captures I and then returns I plus j. So then it gives you another lambda that'll take another integer and then adds the two together. And then, obviously this is pretty trivial, but you can actually use that to do fairly neat things. So some more examples of them. Like say you have some struct value, and it probably has other stuff, but it has some value that you want to sort by. And then in foo, you have some sort of vector of values, and you want to sort them. So a typical use case for a lambda is you write your comparison function in a lambda and pass it to your sorting algorithm. And then even though your val struct does not have a comparison operator, the compiler still knows how to sort it because you gave it a comparison function instead of using the operator. So it'll know to use that function instead. And then it'll take your values from your array, or in this case vector, of values, and it'll take them as the left and right hand side parameters and sort using that. So super useful for that sort of thing, where it's one use. So another cool trick is that captureless lambdas specifically, the ones that do capture you can't do this with, but captureless lambdas can be converted to a function pointer. So if you have something that looks kind of like this, which is some sort of template function that takes a pointer to a function, you can actually add a plus sign in front of your lambda, and that'll get it converted to a function pointer, which is pretty neat. I have no idea why that works, but it's really cool. So state in lambdas is something that can actually be maintained. So if you have some sort of static variable in your lambda and you modify it across calls. So here we have a first call to counter, it'll give you 1, and then a second call, it'll give you 2. So that static int is actually maintaining its state across calls to the lambda. So that's, again, pretty much this code here is getting copy pasted into some sort of struct. And then you have an instance of the struct, and it's working the exact same way. So then if you have another counter, which is equal to it, it's of the same type, because you just copied it. So then they actually use the same static int. So it's almost entirely functionally equivalent to just making some sort of function object. So lambda copyrights, they can be copied by default. This can, of course, lead to dangling references, which I kind of mentioned earlier, where if it's like going out of the lambda will exist longer than the scope it's created in, you have to watch out for that. But there's some unknown cost, because you don't really know how big your lambda is. Since it's some sort of type being generated by the compiler, you don't really know a lot about it. But you can, of course, use size of to figure that out if you really care. But sometimes copying isn't the behavior you want from your lambda. So a neat trick you can do is abolish the copyrights. So you'll need a little bit of setup for it. What these macros do is they basically generate a unique ID with some name, and then concatenate them together into a unique token. And then you can make this no copy struct here. And then what you do with no copy is you just delete all of the copying that you want. So you can't copy it, you can't assign it, but it can be moved because a move isn't a copy. I mean, if you want to disable moving, you can do that as well. And it can be constructed a single time with a default constructor. And then you have this macro here, no copy, where x is used for no copy. And then when you are making a lambda that you don't want copyable, you just put that little no copy there in your lambda capture list. And then it captures an object which can't be copied. And so then if you try to copy the lambda, it will fail to compile. So that's pretty neat. Trick 3, overloading lambdas. So typical functions you can overload, but a lambda doesn't have a name, so how do you overload it? Any ideas? So that'll let it take any type for the parameter, which is kind of overloading, but it's closer to templates than overloading. So this trick, you can actually have it have completely different signatures, like 1 argument and 2 arguments, as an example, which you can also do with generic lambdas with auto ... But with this, you can have, like, if you only want it to work for int and float, for example, instead of any type. So the trick is more templates, because lambdas are not quite like normal functions. Since they're anonymous, you can't easily overload them since they don't have a name, right? So what do? You throw lots of templates at the problem. So this is an example that can overload with 2 types. So what you do is you have this make overload function that you can call with 2 lambdas. So I call them predicate 1 and predicate 2. So those are the template types. And then it constructs an overload object, which is defined up here using them. And so what overload does is it stores values of those predicate types, and then it just forwards any operator parentheses usage to your predicates with the using keyword. So then anytime you try to invoke this object like a function, it will try to resolve it using the parentheses operator of the lambdas that it has. See, and it's inheriting from those 2. So it's multiple inheritance. Everybody's favorite C++ feature. So yes, the solution is really multiple inheritance. There is a use for it. And you can actually, using variadic templates, get this to work for any number of lambdas. So yeah, what you would do there is instead of having like specifically pred1, pred2, you would have type name args ... And then you can use as many as you want. And it works pretty much the same way. So yeah, for example, here you can have this print variable, which is made by using make overload. And then you pass it a first lambda and a second lambda, and then it can print different types of values. But this one only knows what strings are and ints are. So if you try to pass it something that can't be implicitly converted to one of those 2, it won't work. So that's kind of neat if you want to log only certain types of values or something. Yeah. So in C++ 14, of course, you have auto, and so that's a little bit more straightforward. And but yeah, as I say here, overloading can still be useful if you want to constrain it to certain types, because auto will try to use any type. So if you explicitly don't want it to work with certain types or only work like with specific types, so more of a whitelist approach, then it'll work with overloading. So a brief aside is about SFINE, which is a template metaprogramming concept called substitution failure is not an error. So if the compiler is trying to resolve a template substitution and it fails, rather than that being an error, it'll try other instances of the template to instantiate it. So it gives you a lot of compile time information, and I'll probably talk more about it in a future talk. But anyway, an example here is you can have some sort of struct, like isPointer, and then by default it's false. But then we have a specialization for it here, for pointers, and that value is true. So for a real isPointer implementation, you'd need more versions than this, because there's more types of pointers, like for example a unique pointer or a shared pointer. If you want to support those, then you would have to have other versions. But the basic idea is it has some sort of information about the template parameter that you can use. So for example, isPointer for int value is false. For int pointer, it's true. Right? So you can use this to do lots of cool things. Some of the limitations are that it uses templates, which can spike your compile time if you just kind of use this like crazy all over the place. And you can't use runtime values, so it's like a compile time thing. You can't use it like with types that might be different at runtime. So with Lambdas SFINE, Lambdas aren't really templates, right? So you can overload them, and make overload is a template function, and overload is a template struct. So with those, you can use SFINE. So especially with C++ 14 generic lambdas, which use auto, those are even fancier. So here we have make overload. So we can enable it if the type is a pointer for whatever variable is, right? Whatever is being passed in there, var. Then you can dereference var for printing it. And then if it's not a pointer type, so you can see the negation there, then we just print the variable. So that's pretty nifty. You can do things like that. So what this is doing, enable if t is part of the standard library. And basically, it will not compile if the value it's given is false. And so is pointer's value for a var that isn't a pointer type would be false. So enable if t is like enable if true. That would not actually be something that compiles. So as Sphene works, since substitution failure is not an error, it failed to substitute the type in there. So it's going to look for other possible ways that it can compile. So here in this one where it's not a pointer, that one would evaluate to true. So enable if t will compile, and it'll pass the substitution, and then it'll know to use this version. So that's kind of a basic example of Sphene and how it could be useful to you, right? If you want to be able to just log anything, right? Like you can just throw in a pointer, a regular variable, it doesn't matter. It'll still figure out how to print it. So some practical Lambda uses that are more common than something like that would be things like algorithms functions, where you need to use a custom comparator object for sorting a vector or other container. Constructing thread instances. So the way a standard thread works is you have to pass it a function to run on that other thread. And so you can actually use a Lambda function as what you want to initialize if you just have some simple logic that you want running in a different thread. You can also use them to call member functions of a specific object instance. So that makes it easier for threads, because on a thread it's kind of annoying to call a member function of a particular object. So you can have a Lambda function just capture that instance of the object and then call the member function and then pass the Lambda to the thread. And then you're just passing a single function call, and then it's all super easy and the standard thread plays nice and you don't get any errors that you don't understand. It's much friendlier. So an example here is, again, sorting in STL using a Lambda. So it'll sort your vector of ints, but this one's sorted already, so it doesn't matter. You can also use them with variadic templates. So the template types or functions can be used for Lambdas. Variable number of template arguments, such as type name ... args, right? So that's a variadic template. So an example of that is a standard tuple. What a tuple is basically just an object that has one element of each of the types you pass in the template parameter list. So you could have like angle bracket, like std tuple, angle bracket, like int, float, bool, and then it will have one of each of those members in the tuple, and you can access them using standard get. So Sean Parent made a code snippet here, which is called for each argument, and basically what it does is, well, it's not really basic, but you give it some sort of function, right, f, and then any number of arguments, and then it'll pass all of those arguments to f as arguments one at a time. And then all of this other stuff is just to kind of create the machinery in which that can happen. So we have class f here in the template. F is the predicate, so that'll be your Lambda in this case. So it has to be able to accept all of the other types after it in the argument list as parameters. And then it can be any of the following of like a function, a callable object, a Lambda, something that resolves as a function when you pass it an argument in the parentheses. So the next part is the class ... args or type name ... args. They're exchangeable. So it can be any number of types. They can all be different. They can be references, const, doesn't matter. There's a different parameter for each type. So as I said before, a standard tuple can just have any number of these different members, right? And then it does the same kind of multiple inheritance thing, where it'll just inherit from them, generally. So the next thing is in the function's signature, you have an instance of f, right? So the capital F is the predicate's type, and then the lowercase f is the actual instance of it. So that would be the instance of your Lambda. The capital F would be the type of it. So then something like this code snippet here should be able to resolve, right? You have f args, and then where args is whatever type. So then the args ref, this is a universal reference, so it can be an L value or an R value reference. It'll resolve to whatever it needs to kind of work. The reason for this is that, say for example, someone passed in the constant 5, like not a variable set to 5, but like just the number 5. You can't really have a reference to 5, right? Because that's an R value. You can't assign to it or anything. So that's why you need this. It's able to resolve for both L values and R values. Then args are the types of the parameters. So you can see it's any number of types with whatever reference type would be necessary. And then the dot, dot, dot denotes that it's a variable number, so any number of them. And then args with lowercase a is the actual parameters to the function. So then what we can do here inside the body is we have the initializer list of ints. And so that what we're doing there is with the stuff inside, we're actually instantiating an initializer list of ints. So we have to make this call to our Lambda function resolve as a bunch of ints. So we also want to pass all of the different parameters to this function to our Lambda. So we have to create some context where that's valid. And then void just casts it to void. That's not anything clever. And then to create a context to expand the parameter pack. And so it has to work with 0 arguments. That's the other catch. So it's guaranteed correct parameter expansion ordering when we do it this way. So here inside the actual initializer list, we have forward args. So what this does is it uses move semantics, if they're available for a given type, to pass whatever the argument is to your Lambda or other predicate. And then, of course, f is your predicate invoking whatever your callable object was on the forwarded arguments. And then the comma 0 at the end is kind of unusual. What that does is force the expression to evaluate as an integer. Since we're expanding inside an initializer list of ints, all of the expressions have to evaluate to an integer somehow, right? So even if your Lambda returns something, that expression still has to evaluate to an int. So that's what the comma 0 is for. And then at the end, we have the dot, 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 which is in green here. And then that causes the steps to happen for each of the arguments that were passed in. So when we put this all together, we can do for each argument, you pass it a list of arguments with your predicate, and it'll call your predicate on all of those arguments. So that's pretty neat. Any questions?
So the initializer list is required because otherwise the dot, dot, dot expansion wouldn't work?
Right. So the initializer list gives you a context in which the dot, dot, dot is valid. Yep. Other questions? No? Cool. So an example of it is you can do for each argument, you pass it a Lambda, and then you can pass it whatever arguments you want, and then it'll print them all. Yeah. But there are, of course, way more practical things where you want to do metaprogramming across a bunch of different types where you don't even know what the types are. And so you can use this to kind of write functions that'll work on any type and just take all of your arguments and process them. And since Lambdas are auto, it's very straightforward. So it's super useful for metaprogramming. So that's the end of my talk. Lambdas are super cool. If you have any questions, feel free to ask. Cool. Thanks for coming. What? Oh. It's recorded, so I'll post it eventually. Yep.
I didn't know you could have the Lambda take auto as a parameter and pass that as the first parameter to a function. Because it's like it's a different Lambda each time.
Right.
But it doesn't seem to care.
Yeah. There's also a fun bit on overloading Lambdas.
Oh, good.
Yeah.